Chapter 21, Molecular Orbital Theory. Section 21.2, the H2 plus molecule. To solve the Schrödinger equation for the electrons in a molecule, we may construct a trial wave function using the LCAO-MO method and then minimize the trial energy. The essence of the LCAO-MO method is that the molecular orbitals are the linear combinations of the atomic orbitals. MO denotes molecular orbitals, LCAO denotes the linear combinations of the atomic orbitals. For example, the MOs in the H2 plus or H2 molecules can be expressed as this: a linear combination of, well, over here this is just 1s orbital of hydrogen A, this is 1s orbital of hydrogen B, when we have two nuclei A and B. In H2 plus we have only one electron. We can use this diagram to describe this H2 plus molecule. Two nuclei, one electron. The distance between the electron and nucleus A is Ra. The distance between the electron and nucleus B is Rb. The distance between A and B is Rab. Now, what are this C sub A and C sub B? Those are molecular orbital coefficients. Those are just numbers. They put a weight on those atomic orbitals. This 1s A orbital is 1 over square root of pi times e to the power of negative Ra in atomic units. And phi for 1s B is 1 over square root of pi times e to the power of negative Rb. Again, these two equations are in the atomic units. And remember, the fundamental atomic units are this: the charge of electron is 1, the mass of electron is 1, h bar is 1 over 4 pi epsilon 0. This is electric force constant, has a value also of 1 in atomic units. And again, H2 plus contains 1 electron and 2 nuclei. The Schrödinger equation is this: H psi equals E psi. H consists of the kinetic energy operator for the electron, and the attraction this electron feels from nucleus A, the attraction the electron feels from nucleus B, and over here this is uppercase R sub AB. This is the repulsion between the two nuclei. We did neglect the kinetic energy of the nuclei because the kinetic energy of the nuclei is much smaller than the kinetic energy of the electron. Now let's look at the Schrödinger equation for H2 plus. So we have H psi equals E psi. H is the kinetic energy of the electron and the potential energy of the electron plus the nucleus repulsion. We apply that to the wave function, we get the energy times the wave function, after we neglect the kinetic energy of the nuclei. Since the distance between the two nuclei is held constant in the Born-Oppenheimer approximation, we have a simpler Schrödinger equation that focuses on the electronic energy. Over here we have the electronic Hamiltonian applied to psi. H psi equals E psi. This E is the electronic energy. The electronic energy is the Born-Oppenheimer energy minus the nucleus attraction. We simply removed this nucleus attraction from the Schrödinger equation. Now let's look at the LCAO method, linear combination of atomic orbitals. So we express the wave function of the molecular orbitals of this H2 plus molecule to be a coefficient times the wave function of 1s A, and then a coefficient times the wave function of 1s B. So in this equation, well, 1s A is e to the power of negative Ra, 1s B is e to the power of negative Rb. R sub A and R sub B are the distances between the electron and the two nuclei, nucleus A and nucleus B. So R sub A is the square root, over here the sum of three squares. This is x minus the x of nucleus A, y minus the y of nucleus A, z minus the z of nucleus A. And also we have a similar expression for R sub B. So now we have two nuclei. We cannot by default put the both nuclei at the center. None of these two appear at the center now. So usually we treat over here just the midpoint between the two nuclei as the center of the system. Alright, so that's why we have R sub A, R sub B, in this kind of format. Again, the uppercase x, y, z are the Cartesian coordinates of the nuclei. The lowercase x, y, and z are the Cartesian coordinates of the electron. So over here we also have the expression of the uppercase R, which is the distance between the two nuclei, the square root of the sum of these three squares. Again, when we try to solve the Schrodinger equation for the system, usually we'll just assume this A and B have fixed positions. So this uppercase x, y, and z for nuclei A and B are just fixed values. Again, the Schrodinger equation for the electron in the H2 plus molecule is this. We have the electronic Hamiltonian, the kinetic energy of the electron, and also the potential energy felt by the electron. We apply this H to psi, we get E psi. This E is the electronic energy. The wave function of the electron is a linear combination of two atomic orbitals, e to the power of negative Ra, e to the power of negative Rb. Don't worry about the normalization factor. And over here you can see if we move this nucleus B all the way to the moon, and then we have just a hydrogen atom plus another nucleus on the moon. And over here this wave function is just 1sa, e to the power of negative Ra. Now if we move this nucleus A to the moon, then we have a simple hydrogen atom plus another electron on the moon, and the wave function is e to the power of negative Rb. So we're making two different cases, extreme scenarios, to get the over here the basis for the linear combination. So now the molecular orbital is a linear combination of these two atomic orbitals, e to the power of negative Ra, e to the power of negative Rb. And again, C sub A and C sub B are molecular orbital coefficients. And because of the symmetry of this molecule, we know the squared modulus of psi should comprise equal weights of 1sa and 1sb. And therefore, Ca squared is equal to Cb squared. So Ca is plus minus Cb. When Ca is equal to Cb, well, these two 1s atomic orbitals are in phase. The formed MO is a constructive interference of the two AOs. And this MO is symmetric with respect to the center of the molecule. And it's the so-called sigma G bonding orbital. G is the first letter for gerade or G symmetry. Gerade, I think, is a German word that means symmetry or even function. Now we have Ca that can be Cb or minus Cb. When Ca is equal to negative Cb, the two 1s atomic orbitals are out of phase. The formed MO is a destructive interference of these two atomic orbitals. And this MO is antisymmetric with respect to the center of the molecule. And we say this is a sigma U star antibonding orbital. U is the first letter of ungerade in German. Ungerade means odd function, anti-symmetric function. Sometimes we just use U to denote ungerade. This star actually means anti-bonding. So remember, we in the past we used star to denote the complex conjugate, but here, well, this star has a different meaning. So when you see sigma U star, it means this is anti-bonding sigma orbital with a U symmetry or Ungerade symmetry. Oh, I forgot to show you the shapes of sigma G and sigma U star. Over here we have constructive interference between the two atomic orbitals. And over here we have destructive interference between the two atomic orbitals that are out of phase. So in the middle, we have a nodal surface. To normalize the sigma g bonding orbital with this kind of form, we just need to integrate its squared modulus. We expand the squared modulus. We have this 1sa squared, we have 1sb squared, and also we have cross terms. Since this is normalized, so we have 1 and 1 here. Together we have 2, and over here we have another integral, so we just combine this 2 and put it here, and we have integral here. We copy that here. And now we define the overlap integral S sub AB between the two atomic orbitals. S sub AB is defined to be the integral of 1s orbital times 1sb orbital. And therefore, the normalization factor for the sigma g bonding orbital becomes 1 over the square root of 2 plus 2 times SAB. So over here, this is 2 times SAB, and therefore this CG squared is 1 over 2 plus 2 times SAB, and therefore CG is 1 over the square root of 2 plus 2 SAB. And then the molecular orbital becomes this. Now this is normalized. It's 1 over the square root of 2 plus 2 SAB, and then over here we have the constructive interference between these two atomic orbitals, and you can see this MO with a constructive interference in the middle. This is in the middle. We have a overlap between the two atomic orbitals, and this integral S sub AB is called the overlap integral. This integral is always positive. Just because this 1sa function is always positive, this 1sb function is always positive. To normalize the sigma u antibonding molecular orbital, which is a coefficient, times the difference between the two atomic orbitals, again we just need to integrate the squared modulus of this antibonding molecular orbital and set it to 1. Now we expand this wave function squared. We have 1, 2, 3 terms. This integral is just 1. This integral is just 1 because the 1sa wave function is normalized. The 1sb wave function is also normalized. But also we have a cross term over here. Therefore, cu squared times 2 minus this integral of 2 times 1sa times 2 1sb is equal to 1. And we defined S sub AB as the integral of the 1sa orbital times 1sb orbital. And therefore, this cu squared times 2 minus 2 times the overlap integral S sub AB is just 1. Therefore, the coefficient in front of this linear combination in the antibonding orbital is 1 over the square root of 2 minus 2 SAB. And then we have the MO for this antibonding orbital. It's 1 over the square root of 2 minus 2 SAB, and then times the 1sa wave function minus the 1sb wave function. Again, the overlap integral S sub AB, this integral of 1sa and 1sb is always positive. It's just because you can see 1sa is the exponential function, which is positive. 1sb is also a positive exponential function. Therefore, we integrate a exponential function, and over here d tau is the volume element. Now, if we set r sub a equals r sub b, this wave function becomes 0. Because when r sub a is equal to r sub b, we have this two wave functions with the same value, so they cancel, and this side is 0 in the middle. The nodal plane of this antibonding orbital is defined this way. When this is 0, we have a nodal plane, and the nodal plane is right here in the middle between the two nuclei, right in the middle. The normalized sigma g bonding orbital and the normalized sigma u anti-bonding orbital MOs are this two. Sigma g or psi of g as the wave function is 1 over the square root of 2 plus 2 times the overlap integral, and then times the sum of 1sa and 1sb. The antibonding orbital is 1 over the square root of 2 minus 2SAB, the overlap integral over here, times the difference between the two atomic orbitals. we can use this two trial wave functions to calculate the trial molecular orbital energy. So first, let's look at the trial energy of the bonding orbital with the G symmetry or Gerarder symmetry. And it's pretty simple. We just use postulate 4. It's the integral of, over here we have the wave function. Actually, this should be the complex conjugate of the wave function, but since these two wave functions are real functions, so the complex conjugate of this psi of g is itself. And over here we apply the Hamiltonian to the function, and then we can determine this simplified expression for the trial energy. We take this part and this part out. We have 1 over 2 plus 2 times the overlap integral, and then in the middle we have this equation. We can simplify this equation by using shorthand notations. We can do 1sa times h over 1sa applied to 1sa, that's HAA, and then we have this 1sa orbital times the Hamiltonian applied to 1sb, that's HAB, and then we have HBA, which is this times this, and also we have HBB, which is this times the Hamiltonian applied to 1sb. So we have 1, 2, 3, 4 terms over here. HAA is the integral of 1sa and then Hamiltonian applied to 1sa. So really, this is just the energy of the 1s electron in the hydrogen atom. It's negative 1/2. HBB is also negative 1/2. Just imagine you have a hydrogen atom B that includes the nucleus B plus electron. The energy is negative 1/2. Now HAB and HBA, all right, they are just the integral of 1sa, and then over here Hamiltonian applied to 1sb, and here we have 1sb and then Hamiltonian applied to 1sa. So we got two integrals as the cross terms. These two are the same because of the symmetry of this molecule, and these two values will be between 0 and negative 1/2. And because of the symmetry in this H2 plus molecule, we have HAA equals HBB, HAB equals HBA. Also, the physical meaning of HAA is just the energy of the electron in the hydrogen atom A. HBB is the energy of the electron in the hydrogen atom B. So these two are both equal to negative 1/2 atomic units. The trial energy of the sigma G or psi G bonding orbital is this. We have 1 over 2 plus 2 SAB, and then this 4 terms we have negative 1/2 here, negative 1/2 here, and then 2 cross terms. So since HAA equals HBB, we can just write it this way. HAB equals HBA, we can write it this way. So overall, this trial energy for the sigma G bonding orbital is HAA plus HAB over 1 plus SAB. Similarly, the trial energy for the sigma U NT bonding orbital is this: HAA minus HAB. On the bottom, we have 1 minus SAB. So we can compare the trial energy for the sigma G orbital and the trial energy for sigma U NT bonding orbital. So we just need to change this plus sign to minus sign, this plus sign to minus sign. This trial energy for sigma G bonding orbital is more negative than the energy of the electron in the hydrogen atom. So it's more negative than negative 1/2, and that's the reason when H and H plus approach each other from an infinite distance, the energy of the electron keeps decreasing at a rate faster than the increasing of the ion repulsion. So overall, the energy of the entire system decreases, and that's why you can form a bond between the hydrogen atom and a H plus ion. A bond is formed when these two approach each other. Now let's look at this trial energy for the antibonding orbital. It's less negative than the energy of the electron in the hydrogen atom. So it's less negative than negative 1/2. That means if you put the electron in the antibonding orbital, well, it's unfavored energetically. We can define the energy shifts of the two molecular orbitals from the AOs. Alright, so it's delta E sub G, delta E sub U. So now let's look at the molecular orbital diagram for H2+. So we have on the left hand side the hydrogen atom with -1/2 atomic unit energy. Over here we have H+, no electron. Alright, and then let's allow this two to interact. We form two MOs. One is bonding orbital, one is anti-bonding MO. The bonding orbital has a G symmetry or Gerarder symmetry, and this sigma U is the anti-bonding orbital with U symmetry or 1 Gerarder symmetry. This star means anti-bonding. In this sigma G orbital, we have overlap between these two atomic orbitals in the middle. Over here, when we look at the anti-bonding orbital, we have a nodal surface right in the middle between the two nuclei. Now you can see, well, this sigma G has lower energy than the atomic orbital energy. Sigma U has the energy higher than the atomic orbital energy in the hydrogen. So we have a shift here. This delta E sub G is a downshift. This delta E sub U is an upshift. So we can express this delta E sub G and delta E sub U. Delta E sub G is E sub G, you know, the child energy of the bonding orbital minus HAA, which is just the atomic orbital energy. So we plug in the expression of E sub G over here, and then minus the atomic orbital energy. So really it's just -1/2 atomic unit for the hydrogen atom. But for just generality, we'll just keep this H sub AA here. So we take the difference between these two. Over here, this energy is this E sub G. This energy is the atomic orbital energy. So we take the difference from here to here. It's just algebra. We have HAB minus HAA times SAB on top, 1 plus SAB on the bottom. This is less than 0, and that's why actually this E sub G is lower than the atomic orbital energy. And now let's look at delta E sub U, which is defined to be E sub U minus HAA, which is the energy of the anti-bonding orbital minus the atomic orbital energy. So this is positive, and we have this expression as E sub U minus HAA. We kind of just combine this two, some simple algebra. We get HAA times SAB minus HAB over 1 minus SAB. This is greater than 0. So in this fraction, the denominator is greater than 0. SAB is between 0 and 1. So on the bottom, you have a positive value, and on top, you also have a positive value. That's why delta E sub U is greater than 0. So again, delta E sub G is less than 0. So the bonding MO has lower energy than the atomic orbital. And over here, this delta E sub U is positive. So the energy of the antibonding orbital is higher than the atomic orbital. So we have this statement over here. Delta E sub G is negative, delta E sub U is positive. We can easily prove the magnitude of delta E sub G is less than the magnitude of delta E sub U. So in this MO diagram, I intentionally draw this arrow longer than this down arrow for a reason. It's just because SAB is always positive. The overlap integral SAB is usually between 0 and 1, and it's positive. And then we can prove this inequality. Delta E sub G is less than delta E sub U in their magnitudes, because so first we can write this easily. 1 over 1 plus SAB is less than 1 over 1 minus SAB, because this SAB, the overlap integral, is between 0 and 1. And now I multiply both sides by a positive number, which is HAB minus HAA times SAB. So we have this less than this. Alright, and you can see this is the magnitude of delta E sub G over here. It's the magnitude of this. And now if you look at this expression is the magnitude of delta E sub U. So therefore we just proved that the magnitude of delta E sub G is less than delta E sub U. So over here, this shift, downshift, is less than the upshift. So now if you imagine, what if we have 4 electrons? Then we put 2 electrons here, 2 electrons here. And in that case, well, the upshift of the energy is greater than the downshift of the energy. So if you somehow occupy those MOs with 4 electrons, well, it's not going to be favored energetically. That's why we have never observed H2 with 2 minus charges in the real world, because H2 with 2 minus charges is less stable than 2 separate H minus anions.